So good morning, guys. I hope you're having a great week so far. Today we're going to continue our discussion talking about compressible flow. I'm hoping we probably should get into it, get completed with it. But I figured before we kind of keep moving through it, I wanted to take a second to kind of do a quick recap of what I introduced on Tuesday. So I think that's a good place for us to start. One other thing, let me know if it gets a little loud on this side because I have some people here doing some home repair work. So if it gets an issue, I can try to find a quieter spot. So just a heads up. So last time we talked about the main difference that we consider when we're looking at compressible flow is that we have density variations due to changes in temperature and pressure. And since we have those density variations, when we consider our mass balance, mass in is equal to mass out, and we extend it out, we're in terms of density, velocity, and our cross-sectional area. We have to consider not density and velocity by themselves, but their combined product to consider the fact that for steady state flow with a compressible fluid, our mass velocity or mass flux is constant. So in these systems, even though due to pressure variations and pressure drop, we have a decrease in density with as well as an increase in velocity, the mass velocity will remain constant. We also stated that in general, we can assume that a compressible fluid can be approximated as an incompressible fluid if the velocity is low. And that's relative. We'll talk about what that means in a second. And if we have a high velocity, we must apply our compressible flow expressions. And we can quantify this relative velocity using our Mach number, where the Mach number is equal to the fluid velocity relative to its speed in sound, A, at a given temperature and pressure. We can calculate this Mach or speed of sound by the following expressions, where we have gamma, pressure, over density, or instead we can use gamma times the temperature, the ideal gas constant, over the molecular weight. Once again, where gamma is a ratio of the fluid's heat capacities. This is something you can Google. Engineering Toolbox has a list of these. For air, it's always good to have this in the back of your head. Gamma is 1.4. We do a lot of problems with air, similar to doing problems with water, because it's the most common compressible fluid we have to consider. And so with that, combining these expressions with Mach number, we can get a solution for a Mach number as density times velocity squared divided by our gamma times our pressure, or the square root of velocity squared divided by gamma times temperature times the ideal gas constant. Oh, and molecular weight. And the last thing in this introductory section we talked about was the asterisk condition. And this is essentially the fluid properties for a given system where the Mach number is essentially 1 and the speed, the fluid velocity is its speed of sound. When we denote these with an asterisk for a given flow system. Are there any questions on this information? I'll kind of scroll, going a little slow. Is everything we've kind of discussed make sense? Is it clear? And do you have a comfortable grasp of these concepts? Yes, no, maybe so. Go ahead.
I have a quick question. So when you say like high versus low velocity, is that just quantified by the Mach number to determine whether it's high enough or low enough? Okay.
Yeah, that's a good question. I hesitate to give a rule of thumb because it can really depend on the situation, because let's say you have a really low Mach number in a system, but you could also have a very high flow length such that by the end of your system, you have an appreciably high Mach number. Does that make sense? You could start at 0.01 at the entrance to your pipe, but at the end of the pipe, if you're at 0.7, then you really can't assume it would behave as an incompressible fluid throughout the flow system. A lot of times,
that makes sense.
We can consider low velocity is usually like a Mach number less than 0.1. Some people use 0.2, but basically, if you can quantify the Mach number and it's essentially not, if it's essentially far from zero, so to speak, you're probably going to want to consider application of compressible expressions. Any other questions? All right, if not, the next thing we discussed was isentropic compressible flow. Where this was a look at flow through nozzles, where we had a reservoir and a receiver. And when we had 3 sections in this nozzle, we had the converging section, the diverging section, and the throat, the area of minimal flow area. And so for this, we had discussed how we can have one of several situations depending on what's known as the pressure ratio, which, if we're looking at the reservoir as P naught, the receiver as P, it was the ratio of P over P naught. And when our pressure ratio is 1, we essentially have no flow because the reservoir and the receiver are at the same pressure. And then when P naught falls less than 1, we could have subsonic sonic, and supersonic flow, depending on the pressure ratio. And in this, we also considered that there exists a maximum flow rate, where we would consider this to be choked flow, where if we could graph the pressure ratio as a function of the mass flow rate, where pressure ratio of 1 constitutes no flow, and anything less than 1, we see a flow rate. We would find that the curve behaves like this, where we would have a maximum flow rate here, and this section here would be considered choked flow. And this was figure 6.3, your book on page 141. I'm not going to go into too much more detail. We talked about it a good deal on Tuesday. Your synthesis assignment deals in exploring these concepts further in terms of nozzle operation and design. And so I'd be happy to answer any pressing questions, but if not, I think we can go ahead and look at an example. In isentropic flow. However, there are a couple things I should probably mention regarding isentropic flow. So the equations of interest in terms of frictional dissipation and everything for isentropic flow can be found on page 142 and 143. These are equations 623 through 633. And when we're considering essentially flow in these systems, a couple equations rise in terms of importance. The first one being a consideration of what's known as the critical pressure ratio. This is denoted as R sub C in the text, and it's essentially the pressure ratio when P is the asterisk condition, or the pressure necessary to get sonic flow at the nozzle exit. And we can quantify it by the expression 2 over gamma plus 1 to the power of 1 minus 1 minus 1 over gamma. And this is equation 629. We could also consider a look at determining the Mach number for the nozzle. The Mach number squared is equal to 2 over gamma minus 1 times the quantity P naught over P to the 1 minus 1 over gamma power minus 1. An equation 628. Excuse me, 627.
Dr. Lopez, what was the equation number for the previous one, the critical pressure ratio?
It's 629. Yeah, I gave you them because sometimes my handwriting can be a little finicky, and these equations for compressible flow are quite complex. All right. So with that in mind, let's see. The last equation I would consider is looking at another function of the pressure ratio, which is 1 over 1 plus gamma minus 1 over 2 times the Mach number squared, all to the power of 1 over 1 minus 1 over gamma. This is equation 628. There are a couple more for looking at relative changes in pressure and temperature, as well as velocity. But you can find those in your book, and we'll go ahead and look at an example that deals with some of these, just so we can get a little practice. So example 1 here states that air entering a nozzle at 550 Kelvin with a pressure of 20 atmosphere. If the throat area is 1/2 of the diverging section, and assuming the Mach number in the throat is 0.8, what are the values of the following quantities at the throat? So it's, and we're looking for pressure, temperature, velocity, density, and mass velocity. And so it's essentially saying, based off of the incoming air conditions as well as the known Mach number at the throat, what can we estimate for the air properties at the throat? So let's take a look at this example. We know that P naught is 20 atmospheres. T naught is 555 Kelvin. And the Mach number at the throat is approximately 0.8. And we want to know the pressure at the throat, the temperature, the density, the velocity, and the mass velocity. So there's a couple ways that we can do this. We're going to look at a few things one at a time. The first thing we can look at is finding the pressure at the throat. And so using equation 628, which is just shown here, we can solve for that P over P naught, where P is the pressure at the throat and P naught is the incoming pressure. And so I can say P sub T over P naught is equal to 1 over the quantity 1 minus gamma minus 1 over 2 times Mach number squared, all to the power of 1 over 1 minus 1 over gamma. Which equals 1 divided by 1 minus 1.4 minus 1 over 2 times the Mach number squared, which is 0.8, all raised to the power of 1 divided by 1 minus 1 over 1.4. If we do this calculation, we find that P over P naught is equal to approximately 0.656. which implies that the pressure at the throat is 0.656 times the entering pressure of 20 atmospheres, or the pressure at the throat is approximately 13.1 atmospheres. The next thing we can solve for is our velocity using equation 626, which states that u squared equals 2 times gamma times p naught divided by gamma minus 1 times the density naught, or rho naught, times the quantity 1 minus p over p naught raised to the power 1 minus 1 over gamma. There's a lot of exponentials in this one. And so the only thing we need to find to solve for the velocity is the initial density, which we can calculate using the ideal gas expression, P naught, molecular weight over RT. The entering pressure was 20 atmospheres. Molecular weight was 29 kilograms per kilomole. Ideal gas constant, 0.08205. It's liter atmospheres per mole Kelvin. And T was 555 Kelvin. The only conversions I got to do is convert liters to cubic meters and convert moles to kilomoles. So we do this calculation and we can find that the density of the incoming air is approximately 12.7 kilograms per cubic meter. So with this in hand, we can then solve equation 626 for our velocity. Am I going too fast? Do I need to slow down a little bit more? Are you guys following this pace all right?
Just slightly slow down.
Okay, thank you. All right, so in order to solve for the velocity, we have to really take the square root of equation 626. So we end up with the square root of 2 times gamma, which is 1.4, times our P naught, which is 20 atmospheres, divided by gamma minus 1, which is 1.4 minus 1, or simply 0.4, times our initial density, which we just solved for, of 12.7 kilograms per cubic meter. And then we have to multiply this times the quantity all within these brackets, which is 1 minus 13.1 atmospheres divided by 20 atmospheres, all raised to the power of 1 minus 1 over gamma, or 1 minus 1 over 1.4. So we basically have to find the resultant of this value and then take the square root. So if we do this calculation, we should get approximately 1.12 cubic meters, atmospheres per kilogram to the 1/2, which looks really ugly. And so the question is, how are we supposed to end up with a unit for velocity that makes sense? Well, if we look at this, we can say that 1 atmosphere is equal to approximately 101,325 pascals, which is a Newton per square meter. And a Newton is 1 kilogram meter per second squared. So if we do this calculation, we find that what we're left with is meters squared on top and seconds squared on bottom, such that if we take the square root of meters squared per second squared, we're left with meters per second. So we have to multiply our value, 1.12, by the square root of 101,325. And we should get a value around 356 meters per second.
So we wouldn't need to multiply by 101,325 to the 1/2, just 101,325.
No, it would have to be 101,325 to the 1/2. All right, so to solve for the density, the throat, we can use equation 623, which states that the density of the throat can be approximated by the density initially times the pressure ratio in terms of the throat by the entrance, raised to the 1 over gamma power, or 12.7 kilograms per cubic meter times 13.1 divided by 20. They're both atmospheres. The atmospheres cancel, raised to the 1 over 1.4 power. If we do this, we get a density approximately 9.41 kilograms per cubic meter. So the good news then with this is we have both the velocity at the throat as well as the density at the throat. And so to solve for the mass velocity or mass flux at the throat, it's simply the product of these two, or 356 meters per second times 9.41 kilograms per cubic meter, which gives us a value of approximately 3,348 kilograms per meter squared second.
Dr. Lopez, I think on the equation 6.23, we don't divide by 1. I think it's just raised to the gamma power.
Let me take a quick look. It is to the 1 over gamma because the densities have a gamma power on them. So in order to eliminate the power on the densities, you have to multiply both sides of the expression by inverse gamma.
Oh, okay. I see what you're saying. That makes sense.
No. happy to take a look and explain. That's why I'm here. All right, I think the last thing we need to look at is solving for the temperature at the throat, which requires application of 624. And we can get the temperature of the throat approximated by the inlet temperature. Once again, by the pressure ratio to the raised to the power of 1 minus 1 over gamma, or 555 Kelvin times the quantity 13.1 over 20 atmospheres raised to the 1 minus 1 over 1.4 power. We do this and we find our temperature at the throat is approximately 492.5 Kelvin. All right, any questions on that example?
Dr. Lopez, can you discuss the unit conversion that you did to get velocity again, please?
Of course, it's a little strange to say the least, because when you complete your velocity calculation using expression 626, based on the units we have, we end up with cubic meters times atmospheres over kilograms to the 1/2 power, because everything's under the square root. However, if I expand and do a unit conversion between atmospheres and kilopascals, or pascals, I guess, since it's 101.325, a pascal is a Newton per meter squared. So in this sense, then I have, if I break out newtons, I end up with a kilogram times a meter per second squared. And so in this expression, I have a meters cubed here, a meters here, so that's meters to the 4th, divided by meters squared. So I end up with meters squared to the 1/2 power, which is a meter. Everything in these brackets are to the 1/2 power, so I can do my cancellations. So the kilogram cancels, the atmosphere cancels, my Newton cancels. And so what I'm left with is that meters, and then my second squared here, which is also raised to the 1/2 power, and so I'm left with a second. So I end up with the proper units for velocity of meters per second. The only conversion I have to do in terms of calculation is multiplying my final 1.12 times the square root of 101.325. Did that further clarify?
Yes, thank you.
Of course, this is a weird one, to say the least. So I'm happy to, go back and explain anything that you may need or like re-explained. Any other last minute questions or things that we can consider? All right. If not, let's look at our second system under consideration, which is adiabatic frictional flow for compressible fluids. So when I consider adiabatic flow, I'm assuming that if I have flow through the pipe, I can consider my heat transfer negligible, or I can approximate the pipe as an insulated pipe, right? So Q is equal to 0 or negligible. I shouldn't say negligible. And so there's going to be no appreciable heat transfer in the system. However, I'm still going to have friction. And in these systems, in terms of compressible flow, now we're not considering an isentropic system. We have to consider irreversible losses, i.e. friction. And so for compressible flow, the frictional term takes a form that looks like an F times L over RH, where F bar is our average or arithmetic mean friction factor, where if I'm looking at point A and point B, I consider the friction factor at the two inlet and outlet of my system, and then I take their average. Because since the velocity is going to be changing in our system, along with our density, our friction factor can change as well. L is the flow length under consideration, and R sub H is our hydraulic radius once again, which is essentially the diameter over 4 for flow through a circular pipe. And so when we're considering adiabatic frictional flow, there's a lot of expressions that, to be honest, we won't get into. They can be found on page 146 to 148, approximately equations 634 through 636. We're not going to be looking at a whole lot of them. However, the two most important ones that we're going to consider is let's see what equation this comes out to be. Equation 638, which is a comparison of Mach numbers at our flow inlet and outlet, which follows this form, where our friction factor is equal to 1 over gamma times the quantity, 1 over the Mach number, A squared, where in this case, A is our inlet and B is our outlet. So I have 1 over the Mach number of A squared plus 1 over the Mach number of B squared plus, minus gamma minus 1 over 2 times the natural log of our Mach number of B squared times the quantity, 1 plus gamma minus 1 over 2 times the Mach number of A squared divided by the Mach number of A squared times 1 plus gamma minus 1 over 2 times the Mach number of B squared. So a little complicated to say the least. So why might this expression or comparison of Mach numbers at the inlet and outlet be important?
if you don't have the information for diameter or length of pipe, you could back calculate one of those.
Okay. That could be used in that regard, yeah. One important thing that we often have to consider is what are the limitations? Here, I'll do it in red. I like putting questions in red. What are our flow limitations for compressible flow? And so when I consider our flow limitations, the big thing that always comes to mind is when we run into an issue with choked flow, which for a given system, this is going to occur when for any secondary point, that Mach number becomes unity. And so what we can identify is our max conduit length, which tells us what is L max, which results in our outlet existing just at choke flow. And so Tuesday we had talked about how we avoid choke flow. And when we do that is repressurize our fluid after a certain length. And one way to identify that is determine that max conduit length before we have choked flow in our system. And so if I set the Mach number of B equal to 1 for this equation 638, I can identify the maximum conduit length for my system. And I end up with F times L max over RH is equal to 1 over gamma times the quantity 1 over my inlet Mach number squared plus 1 minus gamma plus 1 over 2 times the quantity Ln of 2 times 1 plus gamma minus 1 over 2 times my Mach number initially squared divided by my Mach number initial squared times gamma plus 1 over 2. No, wait, let me double check that. Oh, the 2 went away. That's right, there's a 2 on the denominator. And this is equation 645. One other thing that we have to consider that's important is to find our friction factor, F, we must consider our relative roughness as well as our Reynolds number. Well, we can solve for our Reynolds number times mass velocity times the diameter over the fluid viscosity. However, there's a couple of ways that we can solve for our mass velocity given our Mach number and vice versa. And so for a given Mach number, we can say that Mach number squared is equal to G squared over rho gamma times pressure. Or if we want to solve for our mass velocity, it's equal to the Mach number times the square root of density gamma times pressure. Which, if you want to do it based on temperature and pressure, you end up with an expression that looks like this. This is equations 646 on page 148. And so, as you can imagine, determining frictional dissipation and the implications for it in compressible flow is a little trickier than in compressible flow. Last week, I had you guys work on developing flowcharts so that you can kind of get an idea in terms of the necessary steps for incompressible flow. You can follow a similar structure for compressible flow. However, getting to some of these values is a little less obvious, particularly as it comes to having to rely on mass velocity, because density and velocity will fluctuate throughout the entire system. And so compressible flow calculations must be done with a basis of mass velocity, which typically requires knowing essentially pressure or density and the fluid properties at some point along the system so that it can be initially calculated and then carried through to find your friction as well as these other values of importance. All right. So I know that was quite the alphabet soup. So anything that I can further clarify in terms of questions that you may have, things that you'd like me to clean up in terms of the expressions, or thoughts that you'd like to share and have us consider or discuss. All right, if not,
There's supposed to be a minus sign in equation 6.45. If you have +1, it should be -1.
did I forget the -1?
I think so.
I did. Thank you. All right, now it's -1. All right. So let's take a look at an example. Let's say air flows through a reservoir into a long-shaped pipe. Once it leaves the nozzle, the pressure and temperature in the reservoir are 20 atmospheres, 500 Kelvin, compressed 0.5 at the entrance to the long section of pipe. What is the maximum conduit length in the pipe before the asterisk condition is reached? And we have to worry about dealing with the unfortunate reality of choke flow. So for this question, I'm going to go ahead and throw you guys into breakout rooms. What I want you to do is look at what's provided here in this problem and solve for essentially the right-hand side of the expression on equation 645, meaning you should end up with something that says F times L max over hydraulic radius equals a number. So work together. I'll give you guys a couple minutes and see if you can get that value. So go ahead and take a couple minutes to see what you can come up for that value. How's it going, Aloha?
I'm good, Dr. Lopez. How are you?
I'm okay. Could be better.
How do you like the online classes?
I don't like it as much as in person. However, I think overall the structure I have works. It's just a lot more time intensive and time demanding. I think people, especially in the spring, we failed to underestimate how much more effort and time it takes to prepare a class as well as take a class online.
Yeah, true.
Because there's, as silly as it sounds, there's more onus on students to get the work done because you don't have somebody staring at you in your face, saying, where's your homework? It's all right, here's the window, do it or don't.
Yep. Well, this is my last semester taking a class, so I'm happy on that part.
That's good. All right, that should have been enough time, right?
Yes, so yeah.
Got to find a way to break up class somehow.
Yeah, but like our class with Dr. Naranyan is just 50 minutes. I don't like 50-minute classes. I just feel like, no, it's just too short. Like I remember
No, I love 50-minute classes.
I remember with transport phenomena, Dr. Naranyan would talk at least 2 hours. So it's
that's
so
the problem.
Weird.
Getting Dr. Naranyan to stop talking is the issue.
I'm just not used to, like, right now he never like finishes. We're always breaking.
I'm sure he struggles. He's just like, he wants to keep talking. I like 50-minute classes because I'd rather touch base with people 3 times a week than just 2.
Okay. Yeah.
Because overall the attention and desire to pay attention is higher.
Yeah, true. But it's very funny. We never finished a class in 50 minutes. Like 75 is the best case scenario.
Wow. So he says it's a 50-minute class, but it's really an hour and a half 3 times a week.
Yeah.
I can see that. So how'd it go, everybody?
Not too bad. We got, do you want me to say our number or the right side?
Yeah, you can say your number.
We got 280.02, something like that.
All right. I got 280. All right. Well, I got another number. 280, 280, 280. We got a 280. We got a 281, 281, 281. Nope. Nobody else? Every other group stumped? Sounds like I should put this on a midterm.
That would be fun.
That would be fun. All right. That would be fun. I'll remember that.
Just the number.
Oh no, you got to solve for the length and everything.
Come on.
Right. So let me see if I can jump back into our notes from where we were without my computer catching fire. So, stuff. So that giant mess of an equation ended up being approximately 280, right? So to find our maximum conduit length, we need our friction factor and our hydraulic radius. Now for this system, how do we go about finding our friction factor. Well, we would need to know something about the mass velocity, right? So the mass velocity, ma square root of rho gamma times pressure, which I think the pressure, we can use rho naught, P naught. P naught was what, 20 atmospheres, which rho naught from our example 1 was about 12.7 kilograms per cubic meter. And since we're using the same temperature and pressure, our density should be the same as well. So our mass velocity should be 0.05 times the square root of 12.7 kilograms per cubic meter times our gamma of 1.4 times our pressure of 20 atmospheres under the square root. And we're also going to have to do our same conversion because once again, we're left with kilogram atmospheres per cubic meter. And so we have to do our multiplication like we did in our original example problem. Let's see if I can find it, which was here. And so we have to multiply this system by 101,325 pascals per atmospheres. We do that, we'll be left with kilograms per meter squared second. So let's see what we get. 1.4 times 20 atmospheres times 101,325, square root of that. I end up with approximately 300.1 kilograms per meter squared per second. And so we could solve for our Reynolds number by GD over mu. Mu wasn't provided, so I'm just going to make one up. We'll say it's a 6-inch pipe or about 0.152 meters. We'll say viscosity. We're looking at air, which is fairly low. We'll say the viscosity is really low, or about 0.04 centipoise, or 4 times 10 to the negative 5th kilograms per meter second. So the Reynolds number should simply be 300.1 kilograms per meter squared second times 0.152 meters divided by 4 times 10 to the negative 5th kilograms per meter second. Or about 1.14 times 10 to the 6th. If we assume that we're going to use stainless steel, our K value is 0.00015 feet, which in meters is approximately 4.57 times 10 to the fifth, or negative fifth meters. So our K over D value is going to be 4.57 times 10 to the negative fifth over 0.152 meters. Which is approximately 0.0003. So once again, for this and finding the friction factor, you would use your Reynolds number as well as your K over D value to find that friction factor. So for about 0.003 and about a million, I'm saying about 0.0038 for my F. And we're gonna say 0.0038, which means for this system, since we said F bar times L max over RH equals, what was it, 280? Let me double check my friction factor value. That seems a little high. Oh, no, that works for us. So our hydraulic radius is the diameter over 4. So we have 0.152 divided by 4, which is 0.038 meters, which means L max is equal to 280 times 0.038 meters divided by the friction factor, 0.0038. Which is approximately 2,800 meters. So using equation 645, you really want to solve for that right-hand side. Then you have to identify the friction factor and your hydraulic radius. Once you have that, you can solve for your maximum conduit length. Any questions on that problem?
Dr. Lopez?
Yes.
Where did you get your viscosity value when you calculated your Reynolds number?
I made an assumption and made it up for the sake of the example problem. Full disclosure. In reality, if we were going to do this, I would look that up based off of the given conditions that we have in terms of temperature and pressure. But for the sake of time, I wasn't going to spend the 5 minutes to double check the value. But good question, fair question.
For your average friction factor, why didn't you find it at point A and point B?
In a real problem, I would. That's a very good question. Because for this system, you would have to say what's F of A and what's F of B and do an average. So in that case, you are absolutely right. However, when I'm looking at my system, my Reynolds number will only change due to the viscosity. And so, because when we're looking at Reynolds, we see it's GD over mu. G is going to be constant, D is going to be constant. So the only thing I have to consider is my change in viscosity. So if this was an actual homework problem, you would have to consider the viscosity of both A and B. Solve for your two different Reynolds number based on the difference in flow viscosities. So you'd basically have to solve for essentially the asterisk condition values. You would need to know what P star is and T star is. And with that, you can look up and identify the viscosity at the, find your two Reynolds numbers, find your two friction factors, and take the average. I guess for the sake of argument, in this one, I was assuming that F was just F bar, but in reality, you would need to know what the other viscosity is. So if you want for argument, I can say, let's say the viscosity changes and it goes up to 8 times 10 to the minus fifth. That means even though my Reynolds number 1 is 1.14, this one will be about 5 times 10 to the fifth, or about half the value, which means for solving for that friction, now the K over D is not going to change, but if that changes, my FB would be approximately about 0.004. So if this AFA is 0.038, FB is 0.0004, then that would mean, here I'll separate this out, F bar is then about 0.0039, and then making that correction, you would probably find a slight decrease in that max conduit length. So instead of 2800, it's 2728. A fair point, and one I'm happy to divulge into. The good news is, as we say, the mass velocity isn't going to change. It can't unless you find a way to break a mass balance, but I don't think Dr. O would be very happy about that. And so the only thing you really have to consider is the fluctuation in viscosity, which results in changing your Reynolds to find your 2F values. And what's one of the things, if you do a Reynolds calculation and you end up about essentially 4 times 10 to the 6th or higher, you can probably assume that your F is going to be constant. When you get to that high Reynolds number range, that's another one of those areas where you can make that assumption that F of A is F bar, and you can move on. All good questions. Any other questions? All right, the last thing we can look at for the sake of time and for your homework is isothermal frictional flow. For isothermal frictional flow, the biggest thing that we have to consider is twofold. Our expressions for frictional dissipation and change, such that the big thing you want to look at is equation 649, which states for flow through a pipe coming in at an inlet pressure, leaving at an outlet pressure, we can state PA squared minus PB squared is equal to G squared RT over molecular weight times the quantity of 2 times the natural log of the ratio. And it says densities, but you can also use pressures. And I find it a lot easier using pressures when doing some of the calculations. It also has an LB and an LA. However, to me, that's useless. L's should be understood to be the distance between A and B over RH. So you see that friction term shows up here again. But in this time, what this is considering is the pressure drop due to isothermal flow.
Dr. Lopez, is it a G squared RT over molecular weight?
It is. I promise it's hard to write on this tablet. And so the big thing you have to consider with this is when solving for pressures drop, it requires an iterative process. And so you're going to have to guess essentially a pressure drop and then check that guess with this expression. Also, you have to be careful if you're going to do equation 649 in English units, as you will need to use a G sub C and a 144 in your calculation. And so for English units, I recommend using RS 10.73 cubic feet PSIA per pound mole R. And for SI, it really depends on what pressures you're going to look at, but you can use the 8.314 or 0.08205 cubic meters atmospheres per kilomole Kelvin, depending on what you're looking at. And here, I'll clean that up because I'm sure you probably can't read that chicken scratch. Any questions on that one? I wanted to work an example with you guys. Unfortunately, we're about out of time. But if you want to look through on the slides, I gave you example 3. The actual solution can be found in your text on page 150 and 151. So I would go ahead and give it a shot, and then read through the solution that they have. And so it's an important thing in terms of this. It's just an iterative process, but you're also going to have to do the same things in terms of F, with that being the arithmetic average. But that's really compressible flow. As we explore it, we have the 3 situations: isentropic, adiabatic, and isothermal. For isentropic, we have the expressions that let us look at comparison of values, pressure, temperature, velocity, and so forth, based off of what we knew in terms of our Mach number. For adiabatic and isothermal frictional flow, we have a couple of expressions that take into those losses, the frictional dissipation, into account. With adiabatic, a lot of times we're considering that max conduit length, and for isothermal frictional flow, we look at things in terms of a pressure drop. And we can also consider a max conduit length in this system by setting that PB value to the asterisk condition value. So PB is equal to P asterisk, L becomes L max. So any other questions or things of consideration?
For pressure drop, are we finding the difference between point A and point B, or are we finding the amount at point B?
Most time you're looking at the difference.
Okay, just checking.
However, keep in mind for the expression in 649, it's the difference of the squares. And so it can get a little tricky depending on what you're doing and with your units, because once again, if you start jumping into English, it can get a little hairy. All right, if not, that's all I have for you guys. Have a great rest of your day and a great weekend. Don't forget, I did push back the homework due dates, as well as there is a midterm coming up next week. I will host a review session Monday night, and the midterm is Tuesday night from 6 to 9. Take care, guys, and have a great rest of your day.
Thank you, Dr. Lopez.
You're welcome.